continue with the displacement analysis problem, and today we are going to look at another example of displacement analysis of a constrained mechanism. So, just to give you the overview of today's lecture, we are going to look at the example of a 3R1P chain of type 2. We are going to look at the forward and inverse kinematics problem. So, just to review of what we have discussed previously, we have seen that the determination of the input output relation for a mechanism is the displacement analysis problem, where inputs are actuator displacements and the output is the output link displacement, which can consist of position and orientation of the output link. In the case of robots, the displacement analysis is slightly more involved, in which displacement of the output link can have degree of freedom 2 or higher. So, therefore, we can generate a path, because there are two variables to control. So, we can generate a path in the space in which we are operating. For example, this bin can go through various configurations and move in a path, or maybe this end effector of this robot can move in a path by following successively the displacements at certain points, for which we will have to find out what should be these angles. So, given a path, finding out the angles, or given the angles, finding out where on the path the robot is. This is the problem of displacement analysis. So, we have these forward and inverse kinematics problems. So, forward kinematics states that given the actuator inputs, find the output displacement, and just the reverse is the inverse kinematics problem, which is the second problem of displacement analysis. For a specified output displacement, find out the actuator inputs. So, if I have the bin in this configuration, what should be the throw of these actuators? So, that is the inverse kinematics problem. So, this is our plan which we are following. We are discussing the constraint mechanisms. Subsequently, we will discuss the displacement analysis of robots. So, today we are going to look at the displacement analysis of constrained chain, that and specifically the 3R1P chain of type 2, which I have shown here. We are going to look at both the forward and inverse kinematics problem. So, here I have shown two chains. So, on the left I have shown a chain in which this angle is arbitrary, let us say some angle alpha. Now, we have defined offset for a 3R1P chain as the perpendicular distance from between the two hinges connecting the prismatic pair. So, this is the prismatic pair, this is the line of action of the prismatic pair. So, this is the line of motion of the prismatic pair. This hinge belongs to the prismatic pair, this hinge also belongs to a link which is connected to the prismatic pair. So, the distance perpendicular to the direction of motion of the prismatic pair between these two hinges on the prismatic pair is the offset. So, this is the offset. So, if I am given this angle alpha and this length suppose this length is something specified to us A, then you can very easily see that E is equal to A sin alpha, this being 90 degree, this angle being 90 degree. Now, this offset is something which is fixed, it is a parameter of the chain. A is also fixed, alpha is also fixed, so E is also fixed. So, I can consider an equivalent chain where I replace this inclined link by this link which is perpendicular to the direction of motion of the prismatic pair. So, and call that length as E, the offset. Okay. So, with this understanding, let us see where this kind of chain appears. So, I have taken this excavator example. If you see here, the kinematic diagram is like this. This is a 3R 1P chain. Where the direction of slider motion of the slider can change. So, this we call as the chain 2, 3R 1P chain 2. In 3R 1P chain 1, the direction of slider was fixed. Here this can rotate. This is what we have in this kinematic diagram. So, the direction of the slider can change. So, this is 3R 1P chain 2. So, the output, for example, in this excavator is the angle of this link, the angle of this link. Here I have taken correspondingly this as the output. So, this angle theta 2 is taken to be the output, and this throw of the prismatic pair, which is the actuator in this case, this is the actuator. So, the P pair is the actuator. So, that is considered to be the input. So, let us look at the forward kinematics problem for this chain. So, what we are specified is the input, which is S, which is a throw of the actuator. Here I consider S to be this distance, this length is S. Of course, the part of this may be the length of the actuator and part of it may be the throw, but here we are defining that as s, the total distance as s. So, let me just go back and show you. So, this whole thing is what we call as the input s. So, part of this is the length of the actuator. So, actuator will go from some s min to some s max. So, this may be the throw of the actuator, rest of it might be just the length. So, this is the throw. But S will be defined as I have shown here. So, the problem is, given the distance S, the input S, we have to find out this angle theta 2. So, S is given, we have to find out theta 2, that is the forward kinematics problem. So, here I have this mechanism drawn. I will follow the procedure that we have been following. So, we will write out this distance p q. So, this dashed distance p q since this angle is 90 degree. So, p q square is s square plus e square. So, this is straightforward. So, this is a right angle triangle. So, p q square, the distance p q square is s square plus e square. Now, let us look at this triangle p q r. This triangle p q r. Now, by cosine rule I can easily write p q square is L 1 square plus L 2 square minus 2 L 1 L 2 cosine of this angle, included angle, which is theta 2. So, therefore, cosine theta 2 is nothing but this ratio of L 1 square plus L 2 square minus s square minus e square. So, here I have replaced p q square by s square plus e square and expressed cosine of theta 2 in terms of this. So, what is our input? Input is s, and what do you have to find out? Theta 2. So, we have this equation relating s and theta 2. So, here is s, which is known, the link lengths and offset, everything is known, this is fixed. So, I have the expression of cosine theta 2. So, we have two solutions of theta 2 obviously. So, we can find these two solutions and let us try to understand these two solutions. So, we get theta 2 as cosine inverse of the right hand side. So, when I if I have theta 2 1 as a solution, then minus theta 2 1 is also a solution. So I can have theta 2 1, suppose it is theta star, then theta 2 2 is minus theta star, both will give the same cosine values. Suppose on the calculator you do cosine inverse and you get a certain angle, then minus of that angle is also a solution, as you know. If it is in the first quadrant, then this is the thing. If you have in the second quadrant, so if you have your angle, if this is a solution, then this is also a solution. If you have it in the other quadrant, if this is theta star, this is also the solution. So, let us look at these solutions graphically, let us understand them. So, I have this chain in which S is known. If S is known, this was P and let us say this was Q. So, if S is fixed, then E square plus X square S square, which is PQ square, this length PQ gets fixed. So, if S is fixed, the distance PQ is fixed. Now, we have to locate where the hinge will be assembled with the link 2 L2. So, therefore, this PQ, the link PQ can rotate and it describes the hinge P describes this circle, this big circle. On the other hand, this link L2, so link 2, this moves on this circle. Now, if you have to assemble the mechanism, the hinge on link 2 and the hinge on PQ, they must coincide. So, this is one point of coincidence where what I have shown. The other point of coincidence is here where the circles intersect. So, one of the configurations is shown in black. The question is of the other configuration. Now, the other configuration, in order to understand that, you can very easily see that this link 2 will obviously come here. Now, what about the hinge P on this coupling link? So, that has to go like this. So, this moves on a circle, so this prismatic pair moves on this circle, and now the problem is to find out so this is the circle described by this prismatic pair, the slot. Now, I have to join the coupler at this, making a tangent to this circle. So, let me do that. So, I have to drop a tangent to this circle. And therefore, the mechanism is going to look something like this. So, this is the second configuration of the mechanism. Now, whether it can go from the black configuration to this second configuration, that will depend whether this chain is Grashof or not. So, you have these two solutions corresponding to the two values of theta 2. As you can see, what are the two values of theta 2? So, this is one value, suppose theta star, and the other value is this, which is minus theta star, as we have discussed. These are the two solutions of theta 2, and correspondingly you can find out the configuration of the mechanism. So, here we have looked at these two configurations. Now, let us look at the inverse kinematic analysis of this chain. So, the problem now is we are given this angle theta 2, we have to find out what should be the actuator throw to achieve this angle. So, this is the inverse kinematics problem. So, given theta 2, given this angle, what is S? Find out S, which is the actuator throw. So, given theta 2, find out S. So, what is S? So, we look at this problem quickly. Here we first look at this triangle PQR. So, PQR this triangle here, this is the angle theta 2, which is specified. So, from cosine law I can write PQ square is L1 square plus L2 square minus 2 L1 L2 times the cosine of the included angle. So, that is PQ square. Also we know that PQ square is S square plus E square, we have already seen this, this is a right angle triangle. Therefore, S square plus E square, if I just substitute this here, so S square plus E square is this. Now, remember that we are given theta 2, so theta 2 is specified. We have to find out S. So, this is straightforward. There are two solutions of S, plus minus. Let us understand this graphically. So, we have found two solutions of S as plus and minus. Let us try to understand this graphically. So, just in the passing, let me mention that if this is positive S, then this is negative S. Now, the graphical interpretation of the solution. So, what are we specified? We are specified theta 2. And we have to find S. So, if theta 2 is specified, you can very easily see that this is fixed. This was the hinge P and this was Q. So, P is fixed. P is fixed at this point. What we have to find out is S. How do we do that? Since P is fixed, therefore, this line PQ gets fixed at this. Now, how do I find out S? I know this distance, I know PQ. So, PQ, as we have seen, is known. This distance is known, the orientation of the line is known, everything is known about PQ. Now, how do I find out S from here? Remember that the coupling link, link 3, must be, so this passes through this prismatic pair. This circle has a radius E. Therefore, this coupling link must be tangent to this circle, because this angle is 90 degree. So, E, this is the radial line and this angle being 90 degree. So, this must be tangent to this circle of radius E. So, I can drop two tangents. One tangent I have shown, I can drop another tangent which I am drawing now. So, one tangent is this black configuration, one tangent gives us the black configuration, the other tangent gives us the other solution this is the other solution. Now, here you will notice a subtle thing. What has happened? In the black configuration, S was on this side, the positive side. In this red and blue configuration, this link must be extended in this side and brought here. It is on the other side. The hinge has to be taken to the other side. So, this side is positive, this S is positive, this S is negative. Because it is on the other side of the prismatic pair. Then only this can come and join like this. So, these are the two solutions indicated by this plus and minus of S. You cannot have another solution with plus S. The hinge must go on to the other side. So, that is the negative S solution. Now, whether that is physically possible or not, that is another issue, but geometrically this is the interpretation of the second solution with negative sign. Let us now look at a combination of these chains. So, we have looked at displacement analysis of 4R chains, we have looked at displacement analysis of 3R1P chain, two kinds of 3R1P chain. Now, there are problems in which there is a combination. So, this is what I am showing you here. So, here I have this excavator. I want you to look at this part of the mechanism. So, here we have this hydraulic actuator. So, this is the actuator, and this is the bin. This link is connected to the bin. So, when we have to solve such problems, so it is a combination of a 3R1P chain of second kind and a 4R chain. So, we have a 4R chain and we have a 3R1P chain of second kind. So, we go one by one in steps. So, first we can solve this 3R1P chain. So, given the input, I can find out this angle which I was calling theta 2. Once I know this theta 2, I can go over to this 4R chain. Now, this angle is constant. This angle is constant. So, I can just subtract from theta 2 this angle to get the theta 2 of the 4R chain. Then I solve the 4R chain. So, first I solve the 3R1P 2 chain, and then in the second step I solve for the 4R chain. So, this is true for both forward or the inverse kinematics problem. So, let me summarize. We have looked at the displacement analysis of 3R1P chain of type 2. We have looked at the combination of two different chains for physically relevant problems of displacement analysis. So, with that I will close this lecture.